Good morning. Welcome to the second day of the main conference. My name is Pieter Kempeneers. I'm with the Joint Research Center of the European Commission. And I'm very proud to announce our next keynote speaker. Rosa Baria is the director of the High Performance Computing Software Research Area and manager of the Workflows and Distributed Computing Group at the Barcelona Computing Center. She's one of the key researchers in parallel programming models for multi-core and distributed computing, and she has major contributions to task-based programming models. Today, Rosa will give a keynote from supercomputers to solutions, application workflows for science and society. The floor is yours.
Thank you. Thank you very much, Peter, and all the audience. I guess a bit early, but thank you, everybody. So today I'll talk on a topic that maybe is a bit different for some attendees, but I'll start presenting the status of the deployment of the HPC systems in Europe, thanks to the Euro HPC joint undertaking. And then I'll look into workflows. Workflows being my topic of research in the recent years. I'll try to motivate you on why it's important, the challenges we have. And then I will go into this, how we can manage the workflows like cycle, which has been our contribution in the last years. And then also focus on a use case that can be closer to you, since we have been using Earth observation data in it. Okay. So this is the current status of the HPC systems. The Euro HPC joint undertaking had this mandate to deploy all these systems, petascale systems, pre-exascale and exascale. No? And exascale is 10 to 18, okay? 10 to 18 number of floating point operations per second. Okay? This is the performance of in this case, would be the performance of Jupiter, the machine that has been deployed in Germany and has been inaugurated very recently. No? We have now, you can see this is the first column after the name is the top 500 is the list that lists the systems, usually public systems, I mean the hyperscalers, Amazon, so on, does not put their systems in this list. But these are the lists that are put by the providers on this list. You can see that we have 15 on the top position, 4 in the top 15 positions, okay? Including Mare Nostrum, that it's our system. You see that there are 2 numbers. I will explain now why we have these 2 numbers. The architecture of these systems, most of them have accelerators, GPUs, due to that emphasis on AI, a lot of cases. But also, we have quite a diverse architecture. No? And there will be a new exascale system to be deployed in France. The tender has been just closed, so they have some proposals that they need to evaluate, and they, in principle, will announce the architecture of the system in November in the supercomputing event. So in Barcelona, we have this Mare Nostrum 5 system, which is the 5th of the series of Mare Nostrum since we started the center 20 years ago. In this case, it's composed of multiple clusters. Here I'm showing the 2 production clusters, a general purpose cluster in the table in the top that is structured with Intel processors. And in each node, we have the number of nodes in the left, a number of racks, and then number of nodes in the 3rd column. For each node, we have 2 processors, and each of these processors have 56 cores. So we have 112 cores per node. Okay? And also the diversity on the memory. Some nodes have more memory, and some nodes have high bandwidth memory. And then we have the accelerated system. The accelerated system still have general purpose processors, in this case with 40 cores per processor, but then has 4 NVIDIA GPUs per node. Okay? And this is the one that is more powerful. This is the one that accelerated, that is in the 14th position of the top 500. And we have the other one that is in a bit lower position. Then we have a quantum system also. The quantum system has two systems, in fact, no? The blue and the red, no? Which are the colors of the Barcelona football team, by the way. And so this, there is one chip in each of them. In this case, I think there is one with 10 qubits, another with 5 qubits. Okay, and then all the qubit, the circuit is a very small thing, and you have to deploy all this complex system with the cooler, the cryostate, and everything, okay, the different components of the quantum system. So all these systems are somehow interconnected through the file system. So we have a general parallel file system that connects the 3 clusters, including the quantum. So the data can be shared between all of them. And in the case of the accelerated and general purpose, also are connected through the job scheduler. So you can submit a job that has nodes on the 2 partitions. In the case of in the Mare Nostrum quantum system, the ONA doesn't have exactly the same as LURM, but somehow we will be able to coordinate the jobs in the different systems. So having workflows, my group is also working on workflows that can run part of it in the general purpose or accelerated and in the quantum. So why workflows, no? Well, we see these systems that are increasing in capacity, no? And this doesn't seem to stop. They are still talking in EuroHPC about larger systems. And not only this, we have the digital continuum, which is this environment where we have all the different, from satellites or sensors, antennas, radars, whatever, cameras in the edge, okay? And then we have different type of devices of more low-level capacity close to the edge, different devices, and in the high end, you have supercomputers, the quantum, whatever, no? And we would like to have workflows running across all these systems, okay? And also on the other side, we have that the applications developers every time want to develop more complex applications, applications that are not only high-performance computing applications like simulation of planes or whatever, but also that combine aspects of data analytics and artificial intelligence, and many times in the same workflow. No? And also in the EuroHPC MASP, this MASP is this multi-annual strategic program. I'm part of one of the advisory boards that update this document. As you see, this is the table of the different technologies that the MASP has been considering. And we see workflows appear here as well, no? Workflow managers. And not only this, in the text, if you read, you'll see that the workflows appear, no? Workflows that go across the different systems in the HPC systems, workflows that can combine HPC, AI, and data analytics, workflows that are not only performance, but also energy efficient. So it's an aspect that is in the strategy of the EuroHPC. And also, with regard data, also the MASP also talk about data, okay? So we have growing volumes of data, as you know. And so every time we will have more relevance on systems for high-performance interconnection, storage, AI engines, also efficient data management, no? To control the movement of these high volumes of data, and so on. No? So both workflows and data are seen in this strategic program as very important. No? Then, from our point of view in my group, we've been talking and discussing about this workflow lifecycle manager for lifecycle challenges for some years. And we see that there are different challenges. No? On one side, we have the workflow development, but because if I want to have in the same workflow like traditional HPC modeling with AI and data analytics, usually the programming models that you are using for developing these applications is different. So then we need some kind of look code, some kind of developments that helps on developing this in an easier way. No? Then we have the workflow deployment. If we want to work with end users and applications, usually they are not they don't know how an HPC system works, and it's not that easy. No? So we've been looking into ways that to make more easy the use of HPC, no? How we can deploy in a more easy way the applications in in the HP system. And then we have the workflow operation in general. We want an autonomous operation going beyond the static workflows that can react. No? If there is some change, some data, new data comes from a stream, we can react and start a new type of computation, urgent computing, and not only managing the computing aspects, but also the data management as well. No? And also an important aspect that recently we've been working is on workflow reproducibility, recording automatically the provenance of the workflows. No? And if we talk about what I see as a specific challenges from Earth observation data, we see aspects that probably you know, but I wanted also to emphasize here. We have these large volumes, multimodal of different type, different sources, different formats, and so on, no? And also the latency, no, of acquiring the data. So we need to consider aspects of the data storage and management, as well as integration and harmonization of the data, and data processing for different applications. So there is also a need to support the management of this data from Earth observation through workflows. We can also integrate the same way that we are integrating the computing. No? Then on this project, eFlows for HPC, that we were coordinating from BSc, from my group, I was the IP, we were defining how to manage all these workflows lifecycle with this methodology that we call it HPC workflows as a service. In this case, these workflows were more oriented to HPC, but in general, we work with workflows that can span not only HPC. No? And we were kind of defining, for these different steps that I was mentioning, we were defining methodologies. In particular, for the development, we decompose like the development of the applications of the workflows in 3 parts. The computational part, which is developed with Python scripts that are then run with the PyComs programming model that I will describe in the next slide. Then we have also data pipelines for the movement of data, but also of container images for deployment or AI models in the case of training models. It was described also with Python, but in this case, that were run with Airflow, Apache Airflow. And then we had a top-level workflow with Tosca, which is a standard but is very used in the industry, that describes the whole topology of the workflow and can combine multiple of these. No? Each of these are deployed independently. In the case of the computations, we'll use components that are also in a software catalog. Okay? Or in the case of data, it makes also invocations reference to data sets listed on a data catalog. When we have the workflow developed, we can deploy, store it in a workflow registry, and then we can deploy it. In this case, we were using methodologies based on containers, but not regular containers. We were building containers that were specific to HPC, so they can leverage the features that HPC architectures have. No? And we were then generating an endpoint, so the workflows could be invoked as a service from the end user, simplifying the access to the HPC system. So the user did not have to access the HPC system, could invoke the workflow as a web service. Okay? So I wanted to talk a little bit also about this workflow development phase with PyComs. PyComs is a project that has been under development in my group for more than 15 years. In this case, I'm talking about the Python version, but we also support Java, C, and recently R. And it's based on developing sequential code with annotations. In this case, there's that decorators in Python that the decorators or the annotations identify parts of the code that will be tasks in the execution. And then the runtime looks for data dependencies between the tasks automatically. No? So when a task is called, the runtime will look if there is data that is generated by other tasks that will imply a data dependency with this task. And this creates this task graph, which is the workflow, which each of the nodes represents a task, and the edges represent data dependencies between tasks. And the task graph inherently describes a partial order of the execution of the task. And then the runtime can decide which task can be executed at each time, which can be run in parallel, and which one have to be in a given order. No? It also takes into account the data I mean, the user don't need to move the data himself or herself. The data is automatically moved from the different nodes by the runtime, and also give this illusion that we have a single file system or a single memory. No? And we can run this in HPC, but also in clusters, in standalone servers, in cloud-based servers, and also we have versions that work in the edge-to-cloud environment. As I said, the runtime is the intelligent part of this environment that is able to take care of all the different activities, scheduling, execution, and so on. Okay? If people want more details about this system, I was talking with some people yesterday about this. We can talk further at lunch or coffee breaks. We were also deploying these data management systems through the data logistics service, which was based on Apache Airflow. And as was mentioning before, in this case, we were using this to describe the data movements, stage in, stage out, but also for the deployment, we were using these data pipelines to do the installation of the workflows through containers. And also, if there were workflows that were generating AI models, we were storing them, uploading them in a model repository for further use when was needed this trained model. No? So the same abstraction could be used to move different type of data. So the data, we have the data catalog that lists the data. In this case, it can be many things. The data pipelines that describe with different protocols and formalize the data movements, and the data logistics service, which is the one that makes the movement. And then we have also data provenance. Data provenance is being integrated with the comms runtime. So you can activate it with a flag, and it's able to record all the metadata about the workflow. The data that is accessed, files that are accessed, data that is accessed, tasks that happen, measurements of time, and so on. No? And this is recorded, and we use the arrow crate specification, which was started by the bioinformatics, but now other communities are joining. And they have this workflow hub where you can upload this raw crate, okay? So other users can also download it and check. And also can generate a DOI, sorry. So for example, for reproducibility in articles or so can be used this methodology to provide the reproducibility objects. And we have a reproducibility service that is able to rerun based on a raw crate metadata. And also we have some prototype knowledge graph visualizations that can analyze the metadata in form of a knowledge graph to explore the metadata and validate the experiments interactively. No? Okay, so now I move to the last part of my talk, no, about one of the use cases that we've been working recently. So this is an ecosystem of projects that we've been collaborating. We have on our side the CHIS, which is a center of excellence that focuses on geohazards. Okay, they have volcanoes, earthquakes, tsunamis, and in this case, it has been focusing more on the simulators, on the HPC part of software that is used in these workflows. Then in the eFlows for HPC, we had one of the pillars that was on workflows for earthquakes and tsunamis, and we did some initial workflows that has been later expanded in DTGeo, which is another project that tries to build components of digital twins based on workflows for volcanoes, earthquakes, tsunamis, and also for geohazards. Sorry, for anthropological hazards. Okay? And well, there are other projects in this ecosystem, and we are trying to, we've been in conversation with ECMWF, and we put a proposal that was called Gemini, unfortunately failed, but now we have a small contract with Destination Earth to evaluate these different digital twin components under development to see which of them can be integrated in the future in Destination Earth. No? And this is the study we are doing with this D361A. It's the name of the contract. They didn't allow us to put a more fancy name. So we are evaluating a large set of digital twin components, and we are evaluating the TRL, the readiness of these workflows, of these digital twins, to see which of them could be also if there is any conflict that prevents to the integration in destination Earth, of course, it will not be done. No? So we are evaluating all of them with the idea to select some of them and try to push them into the destination Earth on a digital twin for geohazards in the near future. This is in collaboration with, well, ECMWF made the contract, but there are two researchers at BSc, Josep de la Puente, which is an expert on geohazards, together with me at the BSc, and then Arnau Folk in the CSIC, which is another institution, one is the main institution of research in Spain. And one of these digital components is this DTC-B2, which it tries to forecast the dispersal and ground deposition of ash. No? It's used a simulator, an HPC simulator for 3D, but it's embodied in a workflow that goes through multiple steps, okay? Like getting the data, getting other source data, setting up the multiple simulations, and post-processing the data. No? This is in a very simple way. And PyComs is used to orchestrate the workflows in the HPC system, and also we have this full 3D simulator that is deployed with containers. No? This was taken further in another project, the Get It project, where they added a simulation of Copernicus data. And in this case, data from Sentinel-1A and Sentinel-1B. And then this project has also created this user story in this Destination Earth portal, which I have a small video. I want to mention that there is a, which is not related to me, but there is a demo about this portal later today, like I5, okay? So in this case, this was independent, but I yesterday detected that there is this demo, so you can see also this. And now if the video works, okay. This is more video that I recorded about this user story that is based on this DTC that I mentioned for a specific event that happened on the Christmas of 2018 with an eruption of the Etna. In this case, it was an eruption that was not that big, but was very big in seismicity. And thanks to the Earth observation data from Sentinel-1 and A and B, they have integrated this data into the whole workflow, and they have been able to measure or analyze the ground deformation that was very big, and even kind of split the volcano into two. No? And when this user story, if you're not an expert in volcano, maybe you cannot follow everything, but you can see nice pictures, no? And also, there is also the simulation of the lava flow. This is the actual lava flow that happened in the moment, but also they have another case that will come in the next page about what-if scenarios. No? What would happen if instead of having the eruption in this given point, it was on another point, it is here. And for example, trying to see which eruption could be damaging the population. No? Well, they did it all this, I don't want to go very longer, I think we are out of time. Just that you can look at this yourself. I mean, this is a portal that you can go and move the map and see all the different pages and read separately. So it's a bit the story that has been deployed in this portal. No? So finally, to conclude my talk, on one side we have Europe. The Europe joint undertaking has been able to deploy these world-class supercomputers in Europe, which are serving the whole computing scientific community. The allocations are through public calls that you can apply in groups. For Manuel Mostrom 5, you can apply through the Euro HPC joint undertaking, but also through the Spanish RES, which accepts also participants from that are not Spanish. The Spanish are prioritized, but also non-Spanish can apply. No? With regard workflows, in my perspective, these workflows are very relevant for the progress of the science, no? Especially combining HPC AI and big data. And I have not been able to show today in the talk, but we are working with workflows that have some kind of dynamism that can react to the events that happen. Like in this case, we have one case from an earthquake that we get further information after an event, and we can modify at execution time the workflow. So in general, we think these workflows are very useful for science and progress. No? Earth observation, although in my group personally, we are only having some activity on it through these projects from natural hazards, is also one of the aspects of that these workflows can take into account. Especially because we have an stream data interface for PyCom, so we can acquire data from streams. Okay? So, and as I say, we consider in my group that simplifying this workflow management, this life cycle management of the workflows is very important, so we'll continue working on it. And we are evolving this research into methodologies for the design of digital twins in general. And that's all. Thank you. I don't know if I take more or not. I think we started late.
Any questions from the audience?
Thank you so much for this inspiring direction for parallel computing. I was wondering, could you maybe make it a bit clearer for us how this differentiates from things like Dask or I don't know, Number, that are also sort of toolkits in the Python
Dask
world.
and the other one?
Number?
Number, okay. Dask, you can say that Dask is similar in concept, although we are previous to Dask, I have to say. But what PyComs has, for example, is that in the task you can define constraints. Imagine that your task is using a lot of memory or using multiple cores or specific hardware. You can add a constraint on it, and then the runtime will take care of it. We are also, I think, more tailored for large HPC systems. And we can manage better data distribution and so on. We did also some comparisons, but this, I have to say, that was a while ago, with a library we have for machine learning, which is this lib, which runs on top of PyComs. And we observed that we were able to manage better data management. We were able to run larger data sets and more efficiently. This is because with PyComs, we implement a kind of out-of-core, so we don't have all the memory of the application all the time in memory. We have the data, only the data that we need. And in this way, we were able to run with larger data sets than in Dask. In the case of Numba, we integrated also in PyComs, but for generating vector code or GPU code, okay? So for example, you can have one of our tasks that is annotated with a Numba, and then this will invoke the at compiler time Numba compiler and generate the task able to run on a GPU, which we support, or a vector code. This will be another difference. As far as I know, Dask does not support GPUs. We support tasks that can run in GPUs. Yes? Somebody react, maybe I'm wrong. So, well, there are a few differences. Thank you for the question.
Hi, it's just a little comment. Dask support GPUs.
Okay, I thought this.
And also there's
I saw you fast reaction, so that's why I say I think it supports now then.
And also there's a possibility to limit, say that how much memory you want to use or how many threads you want to use.
For each task?
Yes. No, not for the task workers.
No, in our case we can say,
workers.
Yeah, okay, this is the difference. In our case we can say this for each of the tasks. So if we have tasks that consume a lot of memory, they will be allocated. Imagine you have a task that uses a lot of memory, it can be running a standalone if a node, and if others that do not use that much amount of memory, they can be shared in the same node, okay? So I think this is the difference. The memory of the workers in Dash, yes, you can put it. Okay. Thank you.
Yeah, thank you for the presentation. It was great.
I cannot see who's talking.
Yeah, sorry.
Thank you. Now.
Here. Yeah, I was thinking that, like, what are the main bottlenecks currently? What would you say? You mentioned like many, but what would be the main?
Sorry. Can you repeat? I cannot hear you well.
Yeah, what would be the like main bottleneck in air workflows currently?
In Earth observation workflows?
Yeah.
The main bottleneck, probably it depends if you are streaming directly, which I don't think. If you were streaming directly, will be the bandwidth that you can need to, so it really needs to be real time, no? If you are downloading from one of the providers like Copernicus, then also it can be the size of the data, no? And then you need to use protocols to download the data that support that if the download is interrupted, then that you can continue later. But this exists like grid FTP or so that can download large amounts of data. But of course, the latency of downloading the data, this can be the main bottleneck, I think. Thank you.
Any other questions? If not, then let's thank Rosa again.
Thank you.